Okay, lesson 25 is on the dot product of vectors and the angle between two vectors. This kind of continues our conversation about vectors. It actually completes our little sections on vectors, so we don't have much more with this. So it says vectors can be multiplied in different ways. So one way, which is called the cross product, is used when three dimensions are utilized, and it creates a vector that is perpendicular to both vectors. So if you talk about the cross product of vectors, you can kind of see what it is geometrically, because you can kind of think of the corner of a room. So there's three vectors, and they're all perpendicular to each other. Okay, so the cross product actually helps you find perpendicular, or we use the word normal vectors, right? So luckily for you, we're not going to do cross product, but we are going to do another type of product, which is super simple. So we're going to be discussing something called the dot product. And what this does is it creates a scalar, which is a number. And this number seems completely useless at first. Like, there's no like geometric representation of it, so it doesn't create like a perpendicular vector or anything really like that you can see on a picture. Okay. However, I can assure you that it is used a great deal, and like I said, it's super simple. Okay, so if I have two vectors, u and v, now remember you can see vectors with the arrow over them, or you might see a bolded u. So if you see u dot v, then what we do is we multiply our, I'll call them the x components, right? The first numbers together, so u1 times v1, and then I add it to u2 times v2. Okay, so like I said, very, very simple. So in example number 1, I have 4, 5, and I have -1, 3. So what I'm going to do is I'm going to do the 4 times the -1, and I'm going to add it to the 5 times the 3. So I get -4 plus 15, which creates the number 11. So 11 is the dot product of those two numbers, of those two vectors. All right, so the next one, I'm going to have -6 plus -6, so I end up getting -12. So I just took the two x components, multiplied them together, took those, multiplied them together, and then I added and got -12. Okay, it might be a little more difficult when you see it in the ij form. So if you want to write it like 2 comma -3, and then multiplied, write the dot product with 5i and 0j, so 5, 0. Then we're going to have 2 times 5 added to -3 times 0. So our dot product is 10. Okay, so how do we use the dot product? One of the most important ways of using the dot product is to find the angle between two vectors. So it says if theta is the angle between the non-zero vectors u and v, then cosine of theta ends up being u dot v all over the magnitude of u times the magnitude of v. So if you remember, the magnitude is just the length, right? And we found that in the last section by doing x squared plus y squared, or u1 squared plus u2 squared if you want to. All right, so that means that theta, if you solve for theta, you get inverse cosine of u dot v all over magnitude of u, magnitude of v. Okay, the formula that I typically remember is this one. I don't usually write the inverse cosine one. Okay, so you're going to memorize that one. So number 1, it says find the angle between the two vectors in degrees, round to 3 decimal places if needed. Okay, so what we have is cosine of theta equals u dot v. So I'm going to have 2 times -1 plus 4 times 3. Then I'm going to have the magnitude of u, so 2 squared plus 4 squared, and the magnitude of v, so -1 squared plus 3 squared. So when I work this out, I end up getting, let's see, -2 plus 12, so I get 10, square root of 20, and square root of 10, so square root of 200. And if you rationalize this, you actually get 1 over root 2, which is root 2 over 2. So we want cosine of theta is equal to root 2 over 2. Now you could probably do this without a calculator, but if you need your calculator, that's fine. So you're going to do inverse cosine of root 2 over 2, and you'll end up getting theta is equal to 45 degrees. So make sure you're in degree mode since I asked for degrees. And you can kind of check if you were sketching out these vectors, you have 2 comma 4, and you have -1 comma 3, and yeah, 45 degrees makes sense for that angle. Okay, if it looks like an obtuse angle and you're getting 45 degrees, maybe it's not right, right? But luckily, if you do this formula, there's never going to be one of those situations where you have to like add 180 or anything like that. It's always an angle between 0 and 180 degrees. Okay. So the next one, so let's look at it in the vector form, so 2, 1, and -1, -3, like that. So we're going to do cosine of theta equals u dot v, so -2 plus -3, all over magnitude of u, magnitude of v. So if I do 2 squared plus 1 squared, I get 5. 1 squared plus 9 is 10. So I end up getting -5 over root 50, which is also root 2 over 2, but now it's negative. So when I find theta, I do my inverse cosine again, and this time I get 135 degrees. Okay, so the angle between those two vectors was 135 degrees. All right, so number 2 is probably the most difficult question that you'll have in this section. And I think you do have one of these on your homework. I did not put several of them, no worries. But it says find the vectors v satisfying u dot v equals 10, u is 2, 3, and magnitude squared of v is equal to 17. Okay, so what this ends up being is a system of equations. So we're going to have to use substitution or elimination to find the components for v. Okay, so basically u is some vector u1, v1, or not u1, v1, u1, u2. And v is some vector that's v1, v2. Okay, so when I say u dot v equals 10, what I'm saying is that u1 times v1 plus u2 times v2 has to equal 10. But luckily I know u is 2, 3. So what I really have is 2v1 plus 3v2 equals 10. Okay, so I at least know u. But then I know that the magnitude of v squared, so think magnitude's under a square root, right? So it's like v1 squared plus v2 squared under a square root, but now we're squaring it. That equals 17. So this is not a very simple system of equations because we have these two equations and one of them involves squares. Okay, so it's not like you can line them up and just do your elimination method, right? We can't do that. So we have to do the substitution method. So what I'm going to do is I'm going to solve one of the equations for either v1 or v2. Okay, so let's say I solve this first equation for v1. When I do that, I'm going to have 10 minus 3v2 divided by 2. And now I'm going to substitute it in for this v1. Okay, so it's going to get momentarily a bit messy. So I'm going to have 10 minus 3v2 over 2, everything squared, plus v2 squared equals 17. And I'm going to FOIL it out. So when I FOIL this all out, I get 100 minus 60v2 plus 9v squared all over 4 plus v2 squared equals 17. And I don't like that 4. So I'm going to multiply both sides of my equation by 4. So now I get 100 minus 60v squared, or v, not v squared, v sub 2 plus 9v sub 2 plus 4v sub 2 squared equals 17 times 4, which is 68. And I get everything on one side. Okay, so when I get everything on one side, I have 4v2 squared plus, minus 51, sorry, 60. Did I forget a squared? I did forget a squared. Oh, so lucky I caught that. I could have gone this whole time. It would not have been fun. All right, so I have 13v2 squared minus 60 v sub 2 plus, I believe it's 32, equals 0. And you could try to factor, or you could use quadratic formula. So I personally thought that the numbers were big, so I used quadratic formula. It does factor out. So if you want to do that, go for it. But basically, when you either, so you do factoring or the quadratic formula, you get v2 is equal to 4, but it could also be 8 over 13. Okay, so then we want to find v, and v is two components, right? So one of them has 4, and one of them has 8 over 13 for v2. Well, we still need to find v1. So what do? We go back to where we have this equation and we plug in. So if v2 is equal to 4, then v1 is going to be 10 times 3 times 4 over 2. So I get -1. And for the other one, B1 would be 10 minus 3 times 8 over 13 all over 2. And for that one, it ends up being 53 over 13. Okay, so we get -1 and 53 over 13. But both of these are my solutions. So yes, the -1 and 4 looks very, very nice. You could probably even guess that one using guess and check. But you probably couldn't use guess and check to get the 53 over 13 and the 8 over 13. Okay, so guess and check is not the best method for these problems. All right, so like I said, that one's probably the hardest one that you will have on your homework. The rest of them are pretty simple. All right, so it says if the vectors u and v are perpendicular, then the angle between them is 90 degrees. This means that our formula, right, if theta is equal to 90 degrees, is cosine of 90 degrees equals u dot v, all over the magnitude of u times the magnitude of v. But we know that cosine of 90 degrees, right, if you think about your unit circle, that's the point 0, 1, so cosine of 90 degrees is 0. So in other words, 0 is equal to that whole quotient, u dot v, over the magnitudes. But if 0 equals a fraction, like something over something else, right, it has to be the numerator. So what we know from that is that if our vectors are perpendicular, then 0 equals u dot v. So if u dot v is equal to 0, then our vectors are perpendicular to each other. So you might hear the word orthogonal, or you might hear normal. All of those mean the same thing. Okay, so it says prove that u and v are orthogonal. Okay, so if we're proving that they're orthogonal, then we're going to have 4 times -3 plus 6 times 2. So I'm doing the dot product. Maybe I should write. So I get -12 plus 12. So I get 0. So yes, that means that they are perpendicular or orthogonal. Okay, so this one says find a vector that would be orthogonal to -4, 13. Okay, and you guys are probably very good at this. So we want to think about this getting to be 0. So we're probably going to have some kind of combination of 13 and 4. So let's think about it. If I do -4 times 13 plus 13 times 4, does that get me 0? Yep, sure does. So it's +13 and +4. But that's not the only one. Okay, so you can check, and you could try other things, like maybe I multiply by 2, and I have 26 and 8, right? That still works. So any multiple of this, so if I have any like number out front and I multiply it in, even like 1/5, right? If I take -4, 13, and I have 26 over 5 and then 8 over 5, that still works out. Okay, those are still orthogonal, because basically all we're doing is we have the same vector. So if I sketch it out, I have -4, 13. Let's do 13 here. That's my original vector. And 13, 4 is here, and they are perpendicular to each other. But what about these other ones? Well, if I have 26, 8, it's still the same line. Okay, it's just a lot longer. And maybe I have one that's a little bit shorter, right? That's still orthogonal. So it's still the same direction, it's just their lengths are different when you're multiplying by a scalar. So yes, there are an infinite number of answers. All right, you might also see something about u dot v being parallel to each other. Okay, if they're going to be parallel to each other, that means that cosine, instead of having 90, it was equal to either 180 or 0, and that would give parallel. Okay, so basically if you have u dot v is equal to, so like think about these being here, at 1 or -1, then you would get parallel. All right. Let's do the next thing. So I wanted to do a little bit with kind of an introduction to some things that you're going to do in physics. I'm not going to do as much as Mr. Crawley does, but I just want to kind of give you a little preview. And I meant to edit some of these notes, so I have a little bit of a couple typos in here. So like one of the first typos I have is I meant to, well, I'll tell you when we get there. Oh, here it is. So if he pushes with 250 pounds, so cross that out. because that's a lot of pushing. So we'll cross that out. And then I'm trying to think of any other edits that I had. Okay, so if I see anything else, I'll let you know if you need to cross it out from your notes, because I meant to check it and write out the answers and then adjust, but I forgot to do that before I printed these notes for you for the summer. All right, so the first thing says the vector W pointed straight down shows the weight of a box. So a vector W is going directly straight down, like in the direction of gravity. Okay, so that's going to be the weight of the box. This weight includes gravity. So something that's kind of basic to physics, and some of you that have already taken physics will totally understand this, the others of you might not, is that if something weighs a certain amount in pounds, right, gravity is included. But if we talk about something's mass, mass is in like kilograms or grams or whatever, that doesn't include gravity. Okay, so if we have pounds, then we're including gravity, and this is going to be some kind of force. Okay. This weight vector can be broken into two components. So one of these components is going to be perpendicular to the ramp. So I'll kind of draw this picture bigger. And one is going to be parallel to the ramp. So this is the one that's parallel. And this is the one that's perpendicular. Okay. Right? If you come up with these two values, maybe I'll kind of draw this a little bit bigger here. So if this is our angle theta, that angle theta ends up being right here as well. So this line right here, or this little angle mark, ends up being theta. So let me show you why this is true. So if you have, let's say you have a ramp and it's 20 degrees. Okay, and then we have something going straight down, we have something perpendicular, and so on. Okay. If you have this is going straight down, then we end up having a 90-degree angle there, so this ends up being 70 degrees. But then this angle here was perpendicular. Okay, so that means that this one has to be 20 because it has to make a total of 90 degrees. Okay, so whatever angle you have here, theta, you end up also having in your triangle on the top part. Okay, so we have theta and we have theta. Okay, so when we talk about these two components, okay, we know that we have theta. Let's say we have, we'll call this one x and y. If we're solving for x and y, and we know we have theta here, then I could do, and let's call this w, right? Then I could do cosine and sine using SOHCAHTOA. So what I'm doing is sine of theta equals opposite over hypotenuse, like that. So the x ends up being w times sine of theta. So that's why on the bottom of this little box here, I wrote w sine theta there. Okay, and then you can solve the same way by using cosine, and you end up getting this one, w cosine theta. Okay, so whenever we're talking about the force required to keep the box from going down the hill or the ramp or whatever, that ends up being the one that is parallel. So the parallel force equals force to keep from sliding down. Okay, the perpendicular force is going to be used in just a little bit. So we'll talk about the parallel force first. So number one, so it says a cargo plane is being loaded. The ramp is 3 meters high, which doesn't really matter for right now, and it has an incline of 20 degrees. A box weighs 200 pounds, and a worker plans on sliding it up the ramp. What force is required to keep the box stationary? So what force is required to keep this box from coming back down the ramp? Okay. So if we're finding that, what we're going to do is we always draw our little force straight down. We have a force parallel, so it ends up being this way, and then perpendicular. Okay, and whatever angle we had here, we write right here, so we have 20. We have the weight of the box, which is 200 pounds. That's the force that goes straight down. And we find these two other components. So like I said, you can call them x and y, and you can solve for them, but what it works out to be is this one is always the weight times sine of theta, and this other one is always the weight times cosine of theta. So the force required to keep the box stationary ends up being 200 times sine of, I guess my theta is 20 degrees, right? So if I find that, it's going to be 68. Okay, and the units are kind of weird. Math Excel will put them in already. But this one, like a common unit would be foot-pounds, but I didn't actually have feet, I had meters, so it's going to be meter-pounds, which I know are super weird, but you could have things like that. So forces are usually like Newton meters, foot-pounds, etc., things like that. All right, so it says we know that if someone is pushing a box, it matters how heavy the box is, but it also matters how long the ramp is. So I wrote in here, I have no problem pushing a box that's 200 pounds if I only have to push it for half a foot. For like 6 inches, I'm good. I can do that. But if you ask me to push a box 20 feet that's 200 pounds, I would not be able to do it. Okay, I'm very weak. There's no way that I can do it. That's a totally separate amount of work. Okay, so pushing something 6 inches, no big deal. Pushing something 20 feet, I might need to have some reinforcements, right? So in physics, there's an equation that relates these two things, so the force and the distance. And what that is work. So work is equal to force times distance. So it says, therefore, if I'm pushing a 200-pound box along the ground 6 inches or half a foot, my work would end up being 200 times 1/2, which would be 100 foot-pounds, okay? But if I push the box 20 feet, your work would be 200 times 20, which is 4,000 foot-pounds, okay? Much, much bigger. Okay, so you're multiplying by 40 to get that answer. So it says, what if we move this box up a ramp? Okay, so what if we're pushing a box up the ramp? Well, there's even more work involved because now we're pushing it at an angle, right? So when the weight of the box, has two components, and the formula ends up being, have it on the next page, it's going to be work equals, I always wrote it a different way when I was in physics, so I'm going to write it this way for you. So it's going to be force times distance times cosine theta. So FD cosine theta is what I want you to know. Okay, so what that is the weight of your force, right? So your amount of pounds or newtons or whatever you have. This is the distance from A to B, right? The magnitude of vector AB, and then the cosine theta. So really, this is the formula that I think is best for you to remember. So work equals force times distance cosine theta. So it says find the work done by a force of 12 pounds. Oh, whoops. We're going to skip this one for now. We'll just skip it. I think that's phrased funny. The ones in your Math Excel are like this. Okay, so it says a 2,000-pound car is parked on a street that makes an angle of 12 degrees with the horizontal. Find the magnitude of the force required to keep the car from rolling down the hill. Okay, so we have this car. That's my beautiful car. And it's 2,000 pounds. Okay, you could draw out all of the components if you need to, but we have all of the information that we need. Okay, so our work is going to be the force, which is how heavy it is, 2,000. You're going to multiply by the distance that you're going to, oh wait, never mind. That's part C. Okay, so we do need to draw out our components. So we have these pieces right here. And if you remember, this is going to be my 2,000 sine of 12 degrees. That is the force that keeps it from sliding down the hill. So 2,000 sine of 12 degrees. Okay, and when you find that, it's 415.823 pounds. Okay, so B says find the force perpendicular to the street. I'm realizing that my units were wrong on that last one. Okay, it's not meter pounds actually, it's just pounds on this. It's work that's going to be, sorry, these are the work units. So this is just pounds. Sorry, it's been like 15 years since I've been in physics, so it's all coming back to me. Okay, so anyway, so going back to that problem. So it says find the force that is perpendicular to the street. So when you're finding the force that's perpendicular to the street, that's the other component. So that's the one where we have 2,000 times cosine of 12 degrees. Okay, so the one that is perpendicular is going to end up being 1,956.295 pounds. Okay. So the work done in moving the car up the hill 100 feet, it involved that F cosine theta. Okay, that was where this came from in the formula. It's coming from that force that's perpendicular. That's the force that we're pushing a certain distance. Okay, so my work ends up being F d cosine theta. So I get my 2,000. I have my d, my distance, which is 100, and then I have cosine of 12 degrees. All right, so when I find that, I end up getting 1,956.29.520. And this is now the one that's foot-pounds. Because I'm pushing at a certain distance, and it's a certain weight. So your units involve the force times distance, so foot-pounds. Okay, number 3. So it says to pay for college, Jonathan works in the summer for UPS. Suppose he's pushing a cart full of packages up a ramp that's 10 feet long at an incline of 15 degrees. Okay, the cart weighs 100 pounds. So that's going to be the thing that's straight down. Find the work done in pushing the cart all the way up the ramp. Okay, so we have our force, we have our distance, and we have our theta. So all it is just plugging and chugging, right? F d cosine theta. So the weight of the cart is 100 pounds. The distance you're pushing is 10 feet, but it's not a flat surface, so it's not just force times distance as if it was a flat ground. You actually do have a cosine of some kind of angle, 15 degrees. So you end up getting 965.926 foot-pounds. And then number 4, it says, while pulling a stalled car, a tow truck's cable makes an angle of 50 degrees with the road. If the tension in the cable is 1,600 newtons, how much work is done by the truck when the car is towed 1.5 kilometers? Write your solution to the nearest newton meter. Okay, so it's a little bit different. So we have a car. You could draw an actual car if you want. I know that's a beautiful drawing. And we have a cable that's making an angle of 50 degrees with the road. The tension in the cable is 1,600 newtons. So how much work is done by the truck when the car is towed 1.5 kilometers? Okay, so if you want to find maybe this is kind of the force that we're pulling. Okay, we're pulling it horizontally. So let's say I want to find that, and I want to find it with X. So I set it up, or I call it F if you really want to, I guess. Maybe I will call it F for my force. Okay, so F. So I'm pulling along a horizontal road, so that's the force that I'm looking for. So I'm going to set this up, and I'm going to have my adjacent and the hypotenuse. So I'm going to do cosine of 50 degrees equals adjacent over hypotenuse. And I solve for my force. I think I get 1028.460, and that's in newtons, which is a common unit for force, like pounds and newtons. Okay, and so if I want to find the work done, the work is pulling it horizontally a certain distance. I'm pulling it 1.5 kilometers. So this is the force I'm pulling, and I'm pulling it for this distance. So I'm just going to do the force times distance, which ends up being, let me think, so 1,500 meters, right, times my force, which was the 1028.460. So I changed this to meters. So I end up getting 1.543 times 10 to the 6th Newton meters. Okay. Newton meters are actually joules, if you have heard that before. It's joules. All right, so basically when you're pulling it up, like we were doing here, we were pulling at a certain angle, it's the same equation. Okay, it still ends up being FD cosine theta because I did the cosine theta times the force right here. Okay, so it's exactly the same formula, just a little bit different in the wording. Okay, but I think on the homework, all I have are the ramp problems. And I just have a couple of them. So this section isn't one of the most important sections in the second test that you're going to have. I wouldn't worry about it too much, but at least know the formulas. Work equals force times distance times cosine theta. And know how to find the dot product and the angle between two vectors. That's probably the most important thing. All right, well, good luck on the homework.